Hi, this is Barrett Givens, and in this video, I want to talk about the definition of continuity in a topological space. So if we look at these three statements here in this theorem, the first statement is that F inverse of U is open in X whenever U is open in Y. That's the definition of a continuous function going from X to Y. Okay? So the theorem says, let's say you have a function that's going from X to Y, then the following are equivalent. The following are equivalent, TFAE. So that means these three statements are each equivalent to the other. Each one, it's an if and only if one, if and only if two, two if and only if three, three if and only if one. And since one is actually the definition of continuity, that's telling me that the other two are alternative characterizations of the idea of continuity. Okay? So technically in this theorem, I would have like six things to prove. Like one implies two, two implies one implies three, three implies one, two implies three, three implies two. Okay? But in these things, we often want to kind of be a little bit more clever than that. And so, in particular, in this case, what I'm going to do is I'm going to prove that 3 implies 2, that 2 implies 1, and that 1 implies 3. Okay? And by doing that, I've made a chain of inequalities where I can get from any one of them to any other one. So, like, I haven't directly proved that 3 implies 1, for example, but I'll be able to say, well, 3 implies 2 and 2 implies 1. So by the transitivity of implication, 3 implies 1. Okay, so let's go ahead and do this. Let's start with 1 implies 3. 1 implies 3. I said 1 implies 3, and then I started to write 1 implies 2. 1 implies 3. Okay, so assume 1. So what that means is that what I'm assuming is that if any point during my proof an open set appears in Y, I can assume that its preimage is open in X. It doesn't tell me that I have a U, like there's no U assumed yet. It's just saying like whenever, so like if one happens to come up, then I can use property one. Okay. Now I want to prove 3. So I want to prove 3. So 3 says F inverse of V is closed in X whenever V is closed in Y. So that's another way of saying if capital V is closed in Y, then F inverse of V is closed in X for all possible V. Okay, so let's start with, let's let V subset of Y be closed. And we'll just let it be arbitrary because we want to say this is true for all V. Okay, let's let V subset of Y be a closed set. Then I want to use property one. Well, property one is about open sets, but my V is closed. So I need an open set to apply property one to. Um, how can I get an open set from V? I can take the complement. So let's let U be V complement. Then U is open. So now I've found an open set, so I can apply property one. F inverse of U is open in X. Okay? And now, finally, I'll look at F inverse of V. F inverse of V complement is F inverse of V complement, because that's something we've previously proven, which is F inverse of U. And F inverse of U is open. So F inverse of V complement is open, which means F inverse of V is closed. Okay, so we started with an arbitrary V closed, and then we showed that the inverse image of it was also closed. Okay, and in the middle, we were able to use property one, but we could only use property one. Property one says if you have an open set U. So to use property one, you first have to find an open set U to use it on. And so we found it right here. We said, okay, let's let U be V complement. So we have to find an open set U that we can apply property one to. Okay, let's go ahead and move on to the next one. All right, so I have proven that 1 implies 3. Now let's do 3 implies 2. Proof. 3 implies 2. So I'm going to assume 3 is true. Now, that doesn't mean that I have a closed set V right now. It just means if at some point in my proof a closed set V turns up, then I can apply 3 to it, okay? Because 3 isn't saying you have a closed set V, it's saying if you find one, then its inverse image is also closed. All right, now we want to prove 2. 2 says F inverse of U is open in X whenever U is a basic open subset of Y. So the statement we want to prove is like an if-then statement. If U is basic open in Y, then F inverse of U is open in X. So let's let U, subset of Y, be a basic open set. So I'm starting with a basic open set in Y. And now this proof is going to be just like the proof we just did. So I want to prove that F inverse of U is open, but my assumption is about closed sets. So I need to find myself a closed set that I can apply property 3 to. So let's figure out what closed set could I do. Well, I have a basic open set, so let's let V be U complement. Okay. Then F inverse of U is F inverse of V complement, which is F inverse of V complement. And notice that U is a basic open set, which means it's open in particular, and so therefore V is closed. So our assumption of 3 tells us that F inverse of V is closed. So F inverse of U is the complement of a closed set, which is open. All right, so I finished my proof. I started with an arbitrary basic open set, and then I showed that its inverse image is open. Okay? And in the process, to do that, I had to use property 3. To use property 3, I had to find a closed set somewhere that I could apply property 3 to. And so here it is. I let my V be U complement. Since U is basic open, then V is closed. We don't really have an idea of basic closed, but if we did, maybe this is what it would be. Okay? And this really was just like the previous proof, except for various reasons. I don't know why exactly. I did it in a slightly different logical way, but it's equivalent. So you might want to compare the proof of 1 implies 3 and the proof of 3 implies 2. Compare the two of them and decide which one you like better. And they're really doing the same thing. They're really doing the same thing. So make sure that both ways make sense and maybe think about which way you think is more logical, which one makes more sense to you. But I could have done this proof more the way I did the first one, or I could have done the first one more the way I did this one. They're minor differences, but they're logically the same thing. Okay, in 1 second, I'm going to be back to do the last one. Okay, I'm ready to do the last proof. So we're going to do the proof of 2 implies 1. So I'm going to assume 2. So that doesn't mean that I have a basic open set available. Assuming 2 doesn't tell me that I can assume I have some basic open set U. Assuming 2 means that if in the middle of my proof I find any basic open sets, then I can use property 2. Okay? So I'm trying to prove 1. 1 says F inverse of U is open in X whenever U is open in Y. So that's an if-then statement. If U is open in Y, then F inverse of U is open in X, and that's supposed to be true for all U. So let's let U be an open subset of Y. Okay, and I'm assuming 2. So I'm assuming this property of basic open sets, so I need to somehow find some basic open sets that I can use. And all I have is this set U, which is open. I don't know much about it other than that. But what do we know about open sets versus basic open sets? If I have an open set, can I find some basic open sets? Yes, every open set is the union of basic open sets. So since U is open, we can write U as a union of basic open sets this way. U will be the union over alpha of B sub alpha, where B sub alpha is basic open in Y. Okay? And we don't know what alpha is. You know, this might be over alphas. It might be just a finite union. It could be an infinite union. I have no idea. All right, but now I have some basic open sets. Now I have some basic open sets. And since I'm assuming property 2 is true, I'm assuming that the inverse image of any basic open set is open. And so I'm going to go ahead and say, thus, F inverse of U is F inverse of this union of basic open sets, which by a property that we have previously shown is F inverse of B alpha. It's the union of the inverse image of the B alphas. And now each of these B alphas, I can sort of think of this B sub alpha as being a basic open set. And so applying property 2 using B sub alpha as my basic open set tells me that F inverse of B alpha is open for each alpha. So F inverse of U is a union of open sets, maybe not basic open, but open, is a union of open sets, and hence open. Okay, so I've followed again the sort of same strategy of I'm trying to prove this statement of the form something whenever something. So that's really an if-then statement in disguise. I'm assuming that I'm starting with an open subset of Y, and then I'm proving that its inverse image is open. Okay? And to use property 2, I have to find some basic open sets somewhere that I can apply property 2 to. And so the basic open sets that I found were when I wrote U as a union of basic open sets. So that's how I found some basic open sets that I could apply property 2 to. Okay. And so I have finished all 3 parts of my proof. Luckily, I didn't have to do 6 if and only if proofs. I just had to do 3, implications. And it's a good idea to, when you look at these, think about how the hypothesis is getting used in each case. Okay, thank you for listening.